I want to finish off chapter 2 today. So let's see if we can do that. We were talking about the Dirac delta function well. And so what we said is the potential was going to be equal to minus alpha times this delta of x, where alpha is going to be some positive constant. So that minus sign is what makes it a well. And so the potential is drawn here as a really infinitely narrow, infinitely deep well. And so we were going to try to solve two possible cases. One was where we had a negative energy. So these were going to lead to the so-called bound states. And we went through and we solved that. And actually, we found the solution to the time-independent Schrodinger equation. It's written there. And so here are the corresponding energies. So what we were working on, and I guess what we more or less finished, was the scattering states as well. And so for the scattering states, what we had to do is we had to write down solutions for the wave function to the left of x equals 0 and to the right of x equals 0. In both those regions, the energy, the potential energy is equal to 0. And so we had a pretty simple form for the time-independent Schrodinger equation, which allowed us to write down general solutions right away. And what we realized is that both to the left and to the right of x equals 0, we had waves that were traveling to the right and waves that were traveling to the left. And so our interpretation of these was that let's suppose we have a source of whatever our wave is. And that source is on the left side in negative x, and we're going to associate the right traveling wave as our incident signal. And then the left traveling wave could scatter off some potential, and there could be a reflection. Okay, for x equals bigger than 0, what we decided is that anything that's transmitted through the potential from our source would be our transmitted wave. And if we had no source of signals for x greater than 0 that generated a wave going to the left, then there'd be no reason to expect a left traveling wave on the right side of the potential. And so we could just set g equal to 0. Okay, and so we did all that, and really the rest of the problem was all about applying boundary conditions. Our one boundary for the square wave, the delta function potential is that at x equals 0, that's where our boundary is, and so we required the wave function to be continuous. We also went through some argument to see how does the slope or the derivative of the wave function change at that boundary. And what we found was it changes in this way. This gives the discontinuity in the first derivative of the wave function. And it depends on the form of the potential. For the delta function potential, that gives some non-zero discontinuity that we had to take into account. In any case, we went through and we solved for all these coefficients. If A is our incident wave and B is the reflected wave, that ratio is used to construct the reflection coefficient. In fact, it's the square of this ratio that gives the reflection coefficient, because we have to square our wave functions to get probabilities. So the probability on our well would be given by something like this, where beta, beta is right here. Beta is defined in terms of these parameters. M is the mass of the particle, h bar is a constant, alpha is just the prefactor in front of our potential. It's like the strength of our potential. And then K had energy in it. So the energy appears inside that K. We also could calculate the ratio F over A, which is both right traveling waves, one in positive x, one in negative x. The ratio gives us the transmission coefficient if we square it. And there it is. And then you can notice if I add these two, they add up to 1. And so that's good. The reflection plus transmitted is equal to whatever was incident. Okay, so what I want to do now is say, well, we've considered now the case of a potential well. What if we were to write v of x as plus alpha delta of x, where alpha is still positive? Then our well becomes a barrier. Okay, so what about a potential barrier slash peak rather than a well? What we're going to discover is that we don't have to repeat all of this analysis. A lot of what we did is directly transferable to this problem. Okay, so we're going to say v of x is going to be plus alpha delta x, where alpha is still some positive number. So if I was to write, this would be x, this would be v of x, and kind of draw our delta function, something like this. Okay, well, let's just think about what we would do. We would say, well, I'm only going to think about bound states. And so we would have, sorry, not bound states, only scattering states, I think. Sorry. So yes, in this case, there is no bound state since E will always be less than our potential at x equals 0, because our potential diverges at x equals 0. So we're only going to think about scattering states. When we think of scattering states, we're going to write down a solution for the time-independent Schrodinger equation in this region, in this region. But in those two regions, the potential is 0. That's exactly what we had for the well. So our solutions on the left and right side are going to be the same. We're going to match the wave function at the boundary. That matching is going to lead to the exact same result. We're going to look at the discontinuity in the first derivative of the wave function. And that's the only place where we have to be careful. So when we do that first derivative, we would put in our delta here. However, what we found out is that, where did it go? Sorry. Right, our reflection coefficients are determined by these beta squareds. So beta does depend linearly on alpha. So beta itself changes sign, but if you actually calculate reflection and transmission coefficients, they depend on the square of beta. So whether alpha is positive or negative, it makes no difference. So the scattering, reflection, and transmission off of our well and our barrier are exactly the same. Okay, so I just want to make that point. So however, nothing changes for the scattering states. The solutions to the time-independent Schrodinger equation are the same, because on both sides we have v equals 0 for x less than 0 and x greater than 0. The reflection and transmission coefficients depend only on alpha squared. So its sign is irrelevant. Okay, so without really doing any analysis, what we could say is that a particle incident on v of x equals, say, plus alpha delta x or minus alpha delta x is just as likely to reflect / transmit in either case. Okay, good. So, you might think of the delta function potential as sort of an artificial, infinitely tall, infinitely narrow potential, and it is. But it gives us some insight into the machinery that we would use to calculate more realistic scattering from potentials. So that's what I want to do now, and we're going to go 2.6, and it's going to be the finite square well. All right, and so we did the infinite square well. The finite square well, what we'll do is we'll set it to be equal to 0 most of the place, but we'll have a little step down to some negative potential in some region. And so let's draw what we're going to use for our finite square well. Draw it like this. So here's x, and this is going to be our potential. And the way we're going to define our potential is it's going to be some minus v naught when the absolute value of x is less than or equal to a, and it'll be 0 otherwise. So if we were to mark down, say, a is here, and where's that? Minus a will be right here. So for x above a or less than minus a, we're going to have 0 for our potential. And then if we had, say, minus v naught sitting right here, then this is our potential well. Okay, good. Now, what are we going to do? We're going to do the same sorts of things that we did for the delta function potential. We're going to make sure that our wave function is continuous everywhere, and we're going to look at the continuity of d psi dx. The difference is now we're going to have two boundaries, and so we're going to have to think about those two boundaries carefully. Okay, so let's do bound states first. So bound states are going to be ones where the energy is less than 0. So this is E less than 0, and that's the bound state case. Okay, so bound states. What we should have in mind here is the infinite square well results. The infinite square well, what we know is that we couldn't have our wave function sit outside of the well. So they had to go to 0 at the boundary of the well. But then inside there, we just had like these sine functions and cosine functions that fit inside there. So we could get a certain number of oscillations. And as we increased the number of oscillations that fit inside the well, we went to higher and higher energy states. So we'd expect to see some of that kind of behavior. So let's see. We're going to have to think about x less than minus a. And in that region, the potential is 0. So we've already seen that a bunch of times. So the second derivative of the wave function would be equal to k squared psi. This is the time independent. Oh, sorry. We have a negative energy. This is, I'm going to write it as kappa squared. Okay. Where kappa is equal to square root of minus 2e minus 2me. So it's defined in that way so that, remember, kappa is a positive number because e is negative. Okay, so the solution is psi of x is equal to the general solution is a e to the minus kappa x plus b e to the plus kappa x. But when we were talking about this for the delta function potential, remember, if I had the minus kappa x and I took x to negative infinity, then I would have this divergence. So we threw that away, and we'll do that again. So we're going to keep only the plus kappa x solution for x less than a. Okay. X less than minus a, I should be careful. All right. And then we have to think about the region inside the well from minus a to plus a. In this case, v is equal to minus v naught. And let's see, d2 psi dx2 would be equal to minus L squared psi, where L is going to be 2m. It's E plus V naught divided by H bar. So if I squared L, I could multiply by, let's see, H bar squared over 2m. That would be my kinetic energy. I would have a plus V naught in here. With a minus sign, I'd take that to the other side. I'd get a plus V times psi. So that's the left-hand side of our time-independent Schrodinger equation. And on the right-hand side, we'd be left with E times psi. Okay, good. So, so let's just note that E is negative, but E plus V naught is positive. So L is a positive number. When I take the square root, I'll just get a positive real number. E plus V naught has to be positive because E is some negative number, but I'm going to add V naught. And when I add, I'm not going to add minus V naught. I'm just going to add V naught. And so that is going to be positive by this amount. Okay. Good. So the solution in this region is C sine Lx plus E cos L times X. And this is from minus A to plus A. All right. So I'm going to label these. I'm going to label this as, say, the first region. Here's our second region. And then we have a third region, X greater than A. This is exactly the same as X less than minus A case. Okay, so we would say the third solution is psi of X is equal to F e to the minus kappa X. This is X greater than A. You know, the general solution would have a G plus a G e to the plus kappa X. But again, if we took kappa X to infinity, that would blow up. And so we don't want that, non-normalizable. Okay, good. So we have our three solutions in our three regions. So what we're going to do is we're going to apply boundary conditions. So psi and d psi dx are continuous. So let's go back and look at this. Where was it? Right here. This change in the derivative of x. Well, if v of x is a constant minus v naught, I just take it outside the integral, and then I'm going to have the integral of psi evaluated at epsilon and minus epsilon, but psi is continuous, so it's exactly the same at that boundary. So as I shrink epsilon down to 0, this is going to vanish, and this constant outside is just sitting there. So it all gets multiplied by 0. So let's just make that point that for v of x equal to a constant, I mean, I guess we could be specific, minus v naught, a constant, the delta d psi dx goes to 0 as epsilon goes to 0. Okay, so we've got our machinery. We're gonna make a little simplification that's gonna make the algebra quite a bit easier. So in Griffith's problem 2.1 part C, this is one of the problems from the homework that you just handed in, but it was one of the recommended problems. In that problem, what they say is if your potential is an even function, which ours is, okay? The potential at some minus x is exactly the same as it is at plus x. When Griffiths did the infinite square well, he went from 0 to a, where his well lived, and so that was not a symmetric potential, but this one is. The way this one's been constructed, it is. So if the potential is even, then if you work through problem 2.1c, which is not too difficult actually, then psi is either even or odd. So you can consider those two cases separately. We're going to do the even case. So we'll do the even case, and then the odd case will be homework. Okay, so let's set up the even case. We'll recap what our solutions had to look like. So let's start with x greater than a. X greater than a, we said the wave function was f e to the minus kappa x. And then we had a region in between. I'm actually going to go from 0 to x to plus a. If we're thinking of the even case, I can't use sine because sine's an odd function. So I'm going to take the d cos Lx solution. When you do the odd case, you would take the c sine Lx solution. And to enforce that we have a symmetric or an even wave function, I'm going to say that psi of x is equal to psi of negative x for all x less than 0. That includes the part of the well where we're at minus v naught, and it also includes the part where for x less than minus a, the potential is 0. Okay, good. So this is to ensure that psi of x is even. All right, so now we're just going to enforce our boundary conditions. So continuity at x equals a. All right, so we're gonna take f e to the minus kappa a, and it has to be equal to d cos LA. All right, so d cos LA. Okay, I'm gonna label this 4. The other thing we have to look for is the continuity of both psi and d psi dx. So this equation 4 was the continuity of psi. So now we just have to do the derivatives. When I take the derivative of the f e to the minus kappa x, I just get a minus kappa coming down. So our other boundary condition is going to give us a minus kappa f e to the minus kappa x, but x is equal to a at our boundary. And then we have to take the derivative of the second one. That's going to bring out an L. The cos is going to become minus sine. So I think it's minus L d sine L, and then evaluate at x equals a. Okay, good. So this is our boundary condition for the derivative of the wave function. And I'll call this 5. Okay, so you can see that this is going to be a little tricky to solve. What we're going to try to do is we're going to try to take the ratio of these two expressions. If I take the ratio, I'm going to see some nice cancellations. Okay, so we're going to consider taking 5 and we're going to divide it by 4. Okay, so let's see. I don't care about these minus signs. In fact, what I could just do is I just cancel them right away. All right, so when we take the ratio 5 divided by 4, all of f and e to the minus kappa a are going to cancel. And all that we're going to be left with is just kappa. And then let's see, the d's are going to cancel. We're going to get an L times tan of LA. Okay, so this is L times tan of LA. Now, what we have to remember is that both kappa and L depend on the energy. Where did we define them? There they are. So here's kappa has E in it, and here's L, it has E in it. What we'd like to do is we'd like to solve this equation for the energy of the bound states. But that's not easy to do because I've got an L out here and I've got an L inside the tan function. This is a transcendental equation. There is no like algebraic closed form solution. So this is a transcendental equation in E, since both kappa and L involve E. We have to solve this graphically. And so you can see that already a relatively simple problem is requiring, non-algebraic or numerical methods. Okay, so I'm actually going to write down those definitions of kappa and L again. So kappa was minus 2me square root divided by h bar. And L was square root 2m. It was E plus V naught over h bar. Okay. So we're going to solve this thing graphically, but what I'm going to do is I'm going to define Z equals L times A. And L is right here, so that's the same as A over h bar square root 2m E plus V naught. Okay, I'm also going to define Z naught is equal to A over h bar square root of 2m V naught. So then you can see what's going to happen. If I was to take Z squared and subtract off Z naught squared, I'm going to cancel the potential part, and I'm just going to have the 2me. Okay, so let's see. If I was to do kappa A squared, that's minus 2me over h bar squared. Okay, sorry, is that right? Kappa A squared. I must need an a squared factor in there. Okay, so how am I going to get a minus 2me? Why don't I do the opposite of what I said? Why don't I take z naught squared and subtract z squared? And so that's still going to cancel the v naught. But if I'm subtracting z squared, I'll get a minus e, which is going to give me my result for kappa. And so this is equal to z naught squared minus z squared. Okay, so our original transcendental equation is up here. What I'm going to do is I'm going to multiply both sides by a, and then we can use some of these definitions and some of these results to simplify this expression. So kappa a is equal to LA tan LA. Okay, but kappa a is going to be the square root of z naught squared minus z squared. And LA was defined as z, so this is just z, and that's just z. And so we have z tan z. Okay, good. And so we're getting pretty close to what I want to work with. The last step, I'm just going to divide by z. I'll bring it inside the square root. That'll give me a 1 over z squared. I'll get z naught over z all squared minus 1. Okay, so we're going to divide by z. And so therefore, tan z is equal to the square root of z naught over z squared minus 1. And so this is the transcendental equation that we'll solve. So let's solve this numerically. Okay, so the idea is there's lots of ways you could do this. The simplest way is just to make a plot on you're going to plot two lines. One of your lines is going to be tan z, and the other one is going to be this thing, square root of z naught over z squared minus 1. And you're just going to look for intersections. Wherever those two lines intersect, that's a solution to this equation. So to find the solutions for z, we're going to plot tan z versus z and the square root of z naught over z squared minus 1 versus z. And we're going to look for intersections. So I did this. I just have to get the picture. So let's see if I can find it. Sorry, I want to go back here. Come on. All right, so let's see if I can find it. Algebra. Okay, so finite square well, must have passed it. Here we go. I'm going to copy this. So I think this is copied. And let's see if I can paste it in here. Look at that. Good. All right, so let's have a look at this plot here. The dashed line is tan of z. And so I'm interested in the curved part. These vertical parts are just going to the other pole where it goes instantaneously from plus infinity to minus infinity. So I'm interested in the curved parts. That's the tan function. And then this red line is the z naught over z squared minus 1 all square root. And we can see we get 3 intersections. I've labeled them as n equals 0, 2, and 4, because remember, we're only doing the even solutions. There's a whole nother set of solutions that are odd functions. And those are ones that are going to involve like signs, and they're going to have like the n equals 1 and 3 and so on. Okay, so if you just zoom in, you can find the actual numerical value of these intersections. And I did that. So this one corresponds to Z0 is 1.395. This one corresponds to Z2 is, it looks like it's just a little bit over 4. And it came out to be 4.165. And Z3, sorry, not Z3, Z4. It looks like it's just under 7, 6.831. All right, so already we can see some things that are different than the infinite square well. In the infinite square well, we had an infinite number of modes or an infinite number of states that we could put in. They were all like sign knx, where kn just increased indefinitely for all these integer n's. Here, what happens is eventually we hit 0 and there's no more intersections with tan z. So what's physically happening? Why do you think we've run out of states? Why are there a finite number of states? We started, we said we were going to work with negative energies to get bound states. And so as we go to higher n, what happens to the energy?
It's high enough that it's no longer a bound state.
Yeah, it gets high enough that it's no longer negative, and as soon as it goes positive, we're into the regime of scattering states. So that's exactly what happens. So for a given V naught, we only get a finite number of intersections. And so we have only a finite number of bound states with discrete energy. Okay, so let's see, as n increases, so too does the energy. Eventually, E increases so that it becomes positive. And there are no more bound states. We are into scattering states. And so what we're going to do is we're actually going to try to calculate some of these energies. Okay, so when I made this plot, I had to pick some parameter values to actually generate values for Z naught, I guess specifically Z naught. So let me tell you what I did. I said, following Griffiths, I said, I'm going to choose Z naught equal to 8. But Z naught was defined in this way. So when I made the plot, I said, okay, I'm going to take A and H bar and M all equal to 1. So we're going to take A equal to H bar equal to M equal to 1. So this is all 1. So the square root of V naught is equal to 8. So I essentially was taking, so V naught, I guess, is 64. Is that right? I have a typo in my notes, I think. So this is, oh no, I don't. Good, thank God. Okay, 1 and 1 and 1. I still have a 2 in here. So I square this, 2V naught is 64. Divide by 2, I get 32. That's what I have written down. Okay, good. So this is equivalent to taking V naught equal to 32. All right. So then Z, the way we define Z is A over H bar. We took both of those to be 1. 2 times M is 1, E plus V naught. That just reduces to square root of 2 times E plus 32. But we just wrote down all the values of Z for Z0, Z2, and Z4. There were numbers like 1 point something, 4 point something, 6 point something. So we should be able to find E is just Z squared over 2 minus 32. At the same time, once we found E, we can find kappa. Kappa was defined in this way, but with M and H bar set equal to 1, it's minus 2E square root. Okay, so let's make a table. N equals 0, N equals 2, N equals 4. And I'll rewrite the Z naught, or the Z values that we found, the intersections. These are the same values we wrote on top of the plot. All right, and if we sub in to get the energy, well, let's see what's going to happen here. This is, let's call this 7. If we took this to 7 and I squared it, it's going to be 49 divided by 2 is, I don't know, around 25. So we get some small negative number, right? So we get a negative energy like we expected. The energies I found are E0 was minus 31. E2 was minus 23.3. E3, E4 was minus 8.67. If you look at these, they're changing by about 8. If I add 8 to this, or if I add 8 to this, I'll get here. If I add 8 to this, oh, sorry, no, they're not changing by 8. I take that back. For the infinite square well, the energy was proportional to n squared. So that's probably close to what's happening here, but it's probably not exactly. There's some differences. We could also calculate the kappas. I'm calculating the kappas because what I want to do is I actually want to plot the solutions to the bound states, and we need kappa to do that. Okay, good. So let's just note that where did we define it? Z is equal to L. We'll also need L for plotting our wave functions, but if A is equal to 1, then Z is equal to L. So note that for A equal 1, L is just equal to Z, and we have all of those Z values. So we could say this is also L0, this is also L2, this is also L4. Okay, so let's write down what our solutions for the bound state wave function was. D cos Lx 0 x to a, and then we had this symmetrizing requirement. Okay, so if I was to match the wave functions here, they have to match at A. We already did that. What it does is it restricts the value of F. F is not independent from D. This is psi at A. Well, this is matching psi of x at x equals a. Okay, so I just put in an a here and an a here. These two have to be equal. Solve for f. So what I'm going to do to plot this is I'm going to arbitrarily set d equal to 1 for plotting. So I'm going to plot unnormalized wave functions. Okay. So psi is going to be proportional to, let's see, for f, I'm going to put in 1 e to the kappa a cos LA times e to the minus kappa x. So it's e to the kappa a minus x cos L times a for x greater than a. With d equal 1, we just get cos Lx for 0 to a, and then nothing changes here for x negative. All right. So what I had to do for plotting is I had to break this up into different regions and plot this function over 0 to a, plot this function for x bigger than a, and then take the mirror image of that to make sure it's a symmetric solution. So again, I did this. I just have to go fetch the picture. And so let's see if we can find it. And there it is. I'm going to copy this. And let's see if I can place it. All right, good. Oh, no. Okay, so let's undo that. Okay. So what I want to focus in on is this is a busy plot, but on the horizontal axis, I have x over a. So our well extends from -1 to +1. So that's our well. I've grayed out this other region. So the gray part is the region outside the well where the potential is 0. So let's look at the red line. That's the n equals 0 solution. And it's this single little bump. That looks similar to what we had for the infinite square well. But what's different? What did we require for the infinite square well at the boundaries? Yeah.
The wave function goes to 0.
Wave function goes to 0. So if we look at the boundary here, this is 0. Our wave function does not go to 0 at this boundary. So for a finite square well, we can have our wave function leaking outside the potential. This is the low energy state. E is -31 in whatever units those are. Okay, then we look at the n equals 2 solution. Now we have this thing. Again, our wave function doesn't go to 0 at the boundary. In fact, it gets even further away from 0. And so there's more and more leakage as the energy goes up, as the energy gets closer to the top of the well, the wave function bleeds more and more outside the well. And then that continues. Here's the n equals 4. And now there's quite a bit of bleeding outside of the well. If I was to square these, that square would tell us the probability of where we find our particle. And so we have some finite probability of finding our particle outside of this well. Okay, and so if you were thinking in terms of like a ball rolling through like a valley and it had an energy less than the height, the potential energy of the top of the hill, it will never reach this region, but our quantum particles can escape the well a little bit. What I want to emphasize is that this bleeding outside of the well, it has classical analogs. That's not a purely quantum phenomenon. It's a wave phenomenon. I've got one more picture here to grab. And so let me place it. Maybe I'll place it over here. All right. So I don't want to spend too much time on this picture, but what it is this is a little piece of dielectric, and they're going to excite it with electromagnetic waves at some frequency. And if you pick the frequency right, so that the wavelength is similar to the dimensions of your little dielectric block, it can resonate. So you can make these dielectric resonator. And so somebody's done some simulations of the magnetic and electric fields associated with this little resonator. And the only thing that I want to show is that here are the boundaries of the resonator. That's like a little potential barrier. And the fields lead outside that resonator. Once they bleed out, they exponentially decay, just like our solutions exponentially decay once they get outside the well. In fact, we can literally see that exponential decay right there, e to the minus kappa x. That's the exponential decay once we get outside the well region. Okay, so the electromagnetic fields leak outside of a dielectric resonator. And exponentially decay. This is called, you may have heard the term maybe, evanescence waves, evanescent waves. So the only reason I bring this up is that I don't want to leave you with the impression that this wave function bleeding outside the well is a quantum effect. What's quantum is if our particles were electrons, they have this wave character, and it's the wave character that leads to this kind of effect, just like the EM waves leak outside of the dielectric resonator. Okay. The other quantum thing here is that these wave functions represent a probability amplitude, and the square is a probability density. All right, good. So let's do the scattering states of the finite square well. Oh, my tablet's frozen. Scattering states. Here we go. Okay, E greater than 0. So we're going to play the same kind of game. We're going to have to look in our regions. To the left of minus A, the potential is equal to 0, and psi is A e to the ikx plus b e to the minus ikx, where k is the square root 2me over h bar squared. I guess I usually write this with the square root applied just to the numerator, so I'll write it that way to be consistent. So this time e is positive, so it's not a minus e, it's not minus 2me. This is positive, and so these are our oscillating waves, and so we would think of this as being the incident wave, and this one as being the reflected wave. Okay, and then we look inside the well from minus A to plus A. There, the potential is minus V naught. And so we'll say psi is C sine Lx plus D cos Lx. This is the same that we had for our bound states. So L is 2m E plus V naught over H bar. All right, and then we had X greater than A. Again, this is V equals 0, and we're going to assume no left traveling wave. You know, if you happen to have a source creating a wave traveling to the left in this region, then you can include it, but let's assume that we don't. So our wave function is just going to be f e to the I kx, and this is going to be our transmitted. The goal is to calculate, just like we did for the delta function potential, I want to calculate ratios b over a, and we'll construct a reflection coefficient from that. And I want to calculate f over a, and we'll construct a transmission coefficient from that. So the goal is to find r is b over a squared, and t is f over a squared. Okay, the way we're going to approach it is exactly what we did for the delta function potentials. We're just going to make the wave function continuous at our boundaries, and we're going to make its derivatives continuous. So psi and d psi dx are continuous at x equals plus and minus a. Okay, so let's start with at x equals minus a. All right. At x equals minus a, these two have to be continuous. All right, so we're going to get something like a minus sine of minus LA. It's going to be minus sine LA, that kind of stuff. So we would have a e to the minus IKA plus b e to the IKA is equal to minus CL. Sorry, no L. We're not doing the derivatives yet. We will do that. Sine LA plus d cos LA. All right, I'm going to call that equation 1. We'll have equation 2 here for the derivative. And so the derivative is just going to bring down factors of like minus IK and IK and so on. So we're going to have a, let's see, IKA e to the minus IKA. I see. This one was the plus IKX, so it brings down an IK, and then we put in our boundary minus a, so that's why there's a minus sign here. Okay, so then we'd get minus IKB e to the IKA, and that would have to be equal to, so the derivative of sine will be cos, so we'll get LC cos LA. And then the derivative of cos is going to be minus sine, so we get minus LD sine LA. Oh, right. It's minus sine, but then I put in x equals minus a, so we get a plus. Okay. And then we have to do at x equals plus a. And we'll end up with an equation 3. Okay, this time what we're going to do is we're going to match these two at plus a. So we're not going to have a and b, we're going to have just an f. All right, so at x equals a, c sine LA plus d cos LA must be equal to f e to the IKA, and then we have to do the derivatives. So it should be LC cos LA minus LD sine LA equals IKF e to the IKA. I think that's probably right. All right. So at this point, there's a lot of algebra to do. Okay, so lots of
algebra. And I'm not gonna do 4 pages of algebra with you. However, this is problem 2.32 in Griffiths. And so he suggests a way to kind of proceed with this. So what we're going to do is you can show that C is equal to F e to the IK over L cos LA plus sine LA. So this is one of the intermediate steps. The other one is D is equal to F e to the IKA cos LA minus IKL sine LA. The reason that we would solve for C and D first is because if I want reflection and transmission coefficients, I want the ratios B over A and F over A. I don't want C and D anywhere. So I'm going to eliminate these and then I'm going to sub them back in to say equations 3 and 4. Okay, so we would take these and we could sub into some combination of 1 to 4. And what you can find is F over A is e to the minus 2IKA over cos 2LA minus I L squared plus K squared. It's a complicated little expression. Sine 2LA. So therefore, transmission coefficient is the absolute square of this. So once you get a little comfortable with complex numbers, these absolute squares are really easy to calculate. This exponential is just going to die because I'm going to multiply it by its conjugate, and the exponential of minus 2IKA times the exponential of plus 2IKA, that's gone. In the denominator, we have a real part minus I times, like, minus an imaginary part. But when I take the absolute square, all I have to do is square the real part and add it to the square of the imaginary part. And so this is going to come out to be 1 over cos squared 2LA plus L squared plus K squared over 2KL, all of that squared, sine squared LA. Okay, and so that's our transmission coefficient. Good. And if you go through, there's 2 ways that you could calculate the reflection coefficient. What's the smart way to calculate the reflection coefficient? If I have this one. 1 minus that. Yeah, exactly. That's what you could do. Another way to do it is you could actually find B over A, and it's going to come out to be I e to the minus 2IKA. Griffiths doesn't do this, but I did. But like I said, the clever way is just to take 1 minus the transmission coefficient, since we've already gone through the effort of calculating that. So the denominator is the same as it is for the transmission case. And so then the reflection coefficient is B over A squared. And that's going to be, well, again, the I and this exponential, they're going to die. And so we only get this part in the numerator squared. So I'll write it as, let's see, L squared minus K squared over 2KL. That's all squared. Sine squared, 2LA. And then the denominator is the same as this denominator that we had previously. There it is. And I'll leave it to you to confirm, but if you were to add these expressions for R and T, they're going to sum to 1. Their denominators are the same, so you could just combine the numerators. You just have to take care of the fact that you have a minus k squared here, but that's manageable. All right, so how are we doing time-wise? We have like 9 or 8 minutes left. So I didn't plot the transmission coefficient, but I did grab it from the Griffiths text. And so here it is. Let's grab this thing. Okay, so this is the transmission coefficient. So what you can see is that there are places where the transmission coefficient goes to 1. And that's maybe not super surprising because we have these sine functions in here, and this L, remember, contains the energy. It was like the square root of 2m E plus V naught all divided by h bar. And so the energy is in here. And what Griffiths is doing is plotting this transmission coefficient as a function of energy. And those oscillations are from the cos squared LA and the sine squared LA in the transmission coefficient. And you can find special values where there's perfect transmission. A nice analogy to this is, I'm sure we've all experienced this. If you stand in front of like a large window, it's just these 2 parallel surfaces. If you think about it, we're in air on either side of the window, so that has some index of refraction, and then the glass has a different index of refraction, a bigger one. And whenever you have that mismatch in index of refraction, that's a source of scattering for electromagnetic waves, like light. So that thickness of the glass is like the width of our well. And the light goes in there, and it has a particular transmission coefficient, and it looks something like this. And you can see it's not a perfect transmission. There are places where the transmission goes less than 1, and that could only mean that there's reflection. So if you stand in front of a big window, you can see an image of yourself. That image of yourself is from the parts that are reflecting, but it's mostly transmitting. So you see very clearly through the window, like I can see myself right now. And so there it is. That's exactly that effect. What's different is that for a piece of glass, the thickness might be what, a few millimeters, something like that. But optical frequencies are way up at like 10 to the 15 hertz. So the wavelengths are tiny. The wavelengths are in like nanometers. And so you have a huge number of oscillations in a finite thickness of this glass window. And so the transmission coefficient would look like this, but the oscillations would be super, super high frequency or short wavelength, if you like. And our eyes cannot perceive kind of the oscillations that are happening that fast. Our eyes average that out. And so we don't see that, you know, some colors are dimmer than others through this transmission. But this absolutely is happening when you look through a piece of glass. Okay, so that's kind of an analogy. Again, I want to emphasize that these phenomena that we're talking about now of bleeding out of wells and transmission and reflection coefficients, they're wave phenomena, and there are classical analogs to all of these effects. All right, so that's where I'm going to stop. We have finished now chapters 1 and 2. This is the cutoff for the midterm. Next week, we'll start talking about chapter 3. So start reading chapter 3 from Griffiths. I think Monday is a holiday, is it? Is it Thanksgiving? It doesn't affect us, but I guess it affects other classes that you might be in. So have a good long weekend, and we'll see you on the other side.